So thank you for the very kind introduction, and thank you for everyone who is here at the public lecture at the Platform for Advanced Scientific Computing. It's great to have traveled from Atlanta, Georgia, all the way here to Basel, Switzerland, and I look forward to engaging in a great conversation here. PASC is such an excellent community that is formed, and as we talk this week through high-performance computing and data science, this is such an exciting time to be in this field. My talk today is about massive scale analytics applied to real-world problems. So I think about things such as those of you wearing your health devices, trying to make sense of it. How do we have better health and lifestyle? How do we use social media like Twitter to connect to other people? How do we understand trends? How do we make the world a safer place? And that's the sort of problems that I hope to talk with you today about and share with you some of my interest in this field. It was already mentioned a lot of my background here, and I come from a place called Georgia Tech, where I chair a school that was put together about 10, 11 years ago, really focused on solving real-world problems and solving them through high-performance computing, data sciences, machine learning, and so on. And it's a great set of people that we've assembled, about a dozen faculty members, and we focus on problems ranging from cybersecurity to health informatics, analytics and visualization, machine learning, and we also operate for the U.S. National Science Foundation, the South Big Data Hub, that is a multi-year project run by our school. So it's a great place to work on these at a hub, a city in the U.S. that has so many different sectors associated, from risk analysis, transportation, health, finance, security, and that kind of represents where these analytics and these application spaces converge as we're looking for solving meaningful problems. This is just a quick overview. I have about 115 PhD students in my school, about 150 master's students, and as I mentioned, about a dozen faculty and a number of research scientists. At the end of my talk, I'll show you a little bit more about my own research group that's quite active. And I'm very proud of them because they've really done the hard work that I'll tell you about today. We also have a number of strategic partners in our school. We partner with computer vendors and chip manufacturers such as IBM, Cray, Intel, NVIDIA, and others. And we also work with a number of national laboratories, Pacific Northwest National Lab, Sandia National Laboratories, Oak Ridge, and so on, as well as a number of companies from Northrop Grumman, Booz Allen Hamilton, Accenture, and others, Keysight Technologies, LexisNexis. And these are really at the heart of our getting to real problems that are data-centric, data-focused, and having a very tight collaboration between industry, government, and academia to solve the problems that matter. I'm very excited because in a few months, we'll be moving to our new building in Atlanta called CODA. It's a multi-story tower with attached data center that's going to be at the hub of the Southeast US. And my school will be the beating heart of this new building. So I'm really excited, and I invite all of you, when you fly through Atlanta, as everyone does, look me up, come visit, and I'll give you a personal tour. That said, exascale computing has a focus area in streaming data analytics. And what I mean by that is many problems that affect us today, from trying to understand how disease spreads around the world, global pandemics, looking at understanding and influencing massive social networks, business intelligence, insider threats, transportation and evacuation events, looking at understanding complex life systems, drug discovery, drug design, all the way through having a resilient power grid that gives power important for communication networks, transportation networks, energy production, food production, etc., and on to modeling and simulation of full Economic, social, and political simulations of whole nations are places where we see massive amounts of data of different types, and it's coming at us usually through a fire hose at a very high rate. And what we'd like to do in many of these problems is look for common tools, common motifs for solving these types of grand challenges that we can't just sit back and wait. We need to have solutions today. I talk about this often in ways that I should say I can explain to my mother. She's 84. She's actually attended my talks and asked questions, so I try to keep a talk just, they say, where your mother can understand. Well, this is one of those for real. So I explain these graphs in terms of maybe social networks like Facebook. How many of you are on Facebook right now? Okay. So this is a perfect example. So I may talk about social networks, people, events, friendship edges, but think of that just as a motif for graphs. We can apply that abstraction to a variety of different problems where the nouns in the system, people, places, and things, you think of as a vertex or a person, and then the relationship between them of many different types become edges. So edges could represent transportation routes. They could represent the fact that I made a phone call to you. They could represent an email that I sent. They may have timestamps. They may have different weights to them. They may be directed or undirected. So, for instance, I could friend you, but you may not friend me back. Those are two different types of edges. And so in that way, what we want to do is build up this knowledge. We've heard about Google having a knowledge graph or Facebook using graph search. And what that means is that we're trying to put these relationships together into some sort of framework that we can then analyze or query or use to make decisions. And this is really a type of decision support. But the challenge is really looking at this at scale. Having a small graph is, I can pretty much do anything I want with it. But when I start looking at real-world problems that have billions or trillions of entities, whether it's the IP addresses in cybersecurity or the people in a social network, and these billions to trillions of interactions where I have to make split-second life and death decisions, then I need some new technologies. So graphs are pervasive in this confluence between high-performance computing and data science. For instance, in astrophysics, we may use graphs for outlier detection to try to discover new quarks. We may have massive data sets with temporal variations, and what we may do for graphs in this space is clustering or matching imagery in order to discover those events. In this second example over here, bioinformatics, we may have a problem of identifying drug targets, and we are looking for proteins that are interacting within a cell, and we may have issues with the heterogeneity or the different types of data that we've collected and the quality of those data sets in the experiments that are run. And we may be looking at graph problems such as centrality, what are the most important proteins interacting within the proteome, or clustering of different proteins based on their function, etc. So these are different types of graph problems. And then all the way up to social informatics, where we may be trying to discover emergent communities within social networks, modeling the spread of information. And we really have to, oh, is that my mom? I told her don't call. Okay. Thank you. So the graph problems that we try to look at in social networks model potentially flows, shortest paths, different types of clustering. And so when we talk about massive scale graph analytics, there are many, many, many types of problems, graphs, and algorithms that we need to investigate. So this is really lending itself to many different types of applications, a broad range of applications. This slide has a picture of the September 11th, 2001 terrorist network from the attack on the US, where the hijackers are pictured in a graph and their interactions are given over here. And it's suggested that if there was a way to run between a centrality, a graph analytic based on shortest paths on this network, you could pick out the terrorist cells. This graphic, this graphic down at the bottom here is a published image that represents a motif. For instance, here are two people, and they're bad people. Shh. What they do is they live at a house, one buys a truck, the other is, this one rents a truck, this one buys fertilizer. They're observing a factory because they want to blow it up. Don't tell anyone. And our job is to look through this ground truth over here, observed data, and see if you can do a version of subgraph isomorphism, or can I find this pattern in real data? So when I look for intelligence and surveillance, this has been a thought about doing these massive graphs for now 10, 15 years or more. What I do in these graph problems is really try to figure out what kind of beast do I have. And it requires a lot of decision making in terms of data structures, algorithms, software to solve these real world problems. So for instance, I have to decide from my real problem how to map it into a graph abstraction. And when I do so, I typically am trying to find particular features. For instance, find paths within a graph, find clusters or communities, partitions of the graph, matchings, patterns, orderings. There's all sorts of things that I could look for. No two applications are the same, and I have to really decide what it is, what feature. And in my space, working with everything from health informatics to homeland security, I have to sit down with analysts and talk with them about what it is that they do manually or what it is that they really, really want to find, and then see if there's an algorithmic way to support that. There's a number of graph algorithms. We teach all of our undergraduate computer scientists about these algorithms and many more. So everything from traversing a graph, finding shortest paths, flows, spanning trees, etc., are all the different workhorse algorithms that we have. And then there's a lot of different variants to graphs. I mentioned previously that I could have directed or undirected edges. There could be weights on the edges or counts. For instance, distances on a map would count as a weight of an edge, or commute time along an edge, etc. I may have a sparse graph, so M refers to number of edges, N refers to number of vertices. And if I look at that ratio, a ratio that's a smaller number closer to 1 represents a very sparse graph. A number that looks closer to a higher value, for instance, closer to N, would be a very dense graph. So I could look at that ratio. I could look at whether the graph is static, someone just hands me a data set, or whether it changes over time, like a friendship network that evolves as you have new friends and you lose some old friends. They often don't tell you they're unfriending you, but they do, trust me. Maybe some will after this talk. And so when I look at the different types of graphs that we have, I could have equal degree distribution on the vertices, so every vertex connects to maybe 4 or 5 others, or I could have a wide skew of degree distributions, somewhat similar to a social network where there's a few people who have many, many, many friends, the celebrities or stars, and then I have the average person in the middle, and then a lot of people who just have a few friends. So all of these inputs influence the algorithms that I can achieve and then relate to the types of solutions that I have, whether I can apply sparse linear algebra techniques or ad hoc graph methods. And so this is really a growing and emerging area, and the more that we understand the different types of problems, the better we are and will be at solving them. So here's a way I like to explain what we've been doing in my lab for about the last 10 years when I add the word streaming in here. And I'll explain it very similar to a social network where this is person A, and I often represent the actions or edges as tuples. So person A is going to poke person B at time 1, and that's what that tuple represents. So here's person B sitting over here, and maybe at time 2, that first person is going to send a message to person C. And at the very same time, T2, that person B on the right is going to poke person A back. And so each one of these represents an edge in a graph. And as time continues, time 3, time 4, I may have different edge types, like viewing a wall, posting publicly, etc. And I convert these tuples from that real application, whatever domain it happens to be in, into a stream of edges. So here we have edge 1, edge 2, edge 3, edge 4. It's basically a fire hose of edges. And I've abstracted away my domain to a canonic graph representation. And this is the abstraction that we apply, and this is the hope that we can build computers that are able to accept in these edges and perform graph algorithms well. And what they do is, in their memory, they think about the graph that they're holding. So this is a cartoon of a graph. The colors represent types of vertices and types of edges, and whatever type of graph that I've chosen. And that machine is going to hold on to those edges as this high rate is injected into the machine. And then I have analysts, many smart people, who ask questions of that graph, and maybe they ask questions concurrently or many different questions all at once, question 2, question 3, and they take their question from their domain. For instance, in these electronic health patient records, can I find a connection between some trait and a disease among this population? Or are there characteristics that make these medications more effective than others within this population set? The challenge here is to come up with a machine and co-design a machine that's really good at graph algorithms, because up to today it's been quite a challenge. Most of the machines that we have do very well on regular problems where we have dense matrices or regular ordering, and we have a lot of features like superscalar execution, multi-core caches, prefetching that work great on a variety of high-performance computing and scientific computing problems. But when I give these graph problems, we often find challenges in the performance. And so this is the hope of the system. Now, just to give you another application that we've worked on, this is trying to look at social media and ask the question, is there any good that can come out of it? Okay, so to explain this a little further, maybe about almost a decade ago, my students who were new on Twitter were sitting around the lab and trying to decide, is Twitter good for anything? And those of you that know me, I've been tweeting for a while, I'm still not quite sure. But we were the first group that decided that we wanted to take a full take of tweets, public tweets, that at the time were going into the Library of Congress in the US. And we wanted to see, could we have useful information come out of it? So we took the tweets, and the followers and followees, and we looked at a couple breaking events in fall 2009. So this was some time ago. And I'll give you an example of just one of them. H1N1 was, if you recall, a time when there was a global pandemic of an influenza virus that was conjectured going to have mortality rates in the double digits of the world population. Everyone was scared. This was coming from South America. There was a lot of people very scared by it. And we asked the question, how do you figure out who is going to be most influential on getting the real news? Not fake news, not propagated news, but how do you find sources in, say, this social media space to figure out who to listen to? This is kind of like a breaking event. You want to dial your radio and listen to a channel that is going to be the primary source. How do you figure it out on the fly rapidly? So we took about several terabytes of data from a few months of tweets in near real time. We put it into an advanced supercomputer, a multi-threaded machine from Cray at the time, and we constructed a graph on the fly, and then we ran an analytic called between-us centrality. And between-us centrality is conjectured to find influential tweets, handles, or actors within a graph based on shortest paths. It was an analytic that was designed by sociologists back decades ago, and then the algorithms that support it turned out to be based on counting shortest paths within a graph that go through particular vertices. And this analytic has been applied to finding influential jazz musicians, looking at HIV transmission in jail populations, looking for important patents within collections of patents, important citations in literature. It's been applied as an ad hoc measure of finding important things quickly. So we did this experiment, and we came up with the top 15 Twitter handles here for this breaking event. And a lot of them made sense to us. It meant that we have more confidence that our method was working. This was the first study ever to analyze a full take of tweets, the public tweets from Twitter. And some of them made a lot of sense. For instance, in Atlanta, I live across the street from the CDC, and I noticed the top one was CDC. I saw flu.gov, which was also the US government, the New York Times, CNN, also in Atlanta. So I saw a lot of news sources, Time, and government sources, CDC Emergency, CDC eHealth, etc. And that was great. But also I noticed a couple strange things, like official PACs, number 3. Has anyone heard of that handle? Anyone? Of course not. And you would never think to tune into that group. It turns out that this was the penny exchange arcade, a set of mostly adolescent boy gamers who happened to be in Seattle, Washington during the outbreak of H1N1. And they started tweeting to each other, hey, I got sick and I went to the hospital. It was H1N1. And they tweet to their buddies, do you have it too? Yeah, I got it. What are the symptoms? Well, here's what's happening. This is what it does. And they started tweeting some more. Hey, did you die? No. Did you die? No. And so it turned out to be one of the most important sources of understanding within a group the effects of H1N1 and realizing that the mortality rate was exaggerated, and it turned out not to be as a pandemic as was predicted. So this is an example of, in hindsight, if you want to tell the news, you could go and do a big forensic analysis and try to identify this. But on breaking events where you want to figure out who do you listen to, no one would have ever thought to listen to this group, and it turned out to be one of the most influential, even more influential than CNN and Time. But in these types of analyses, you also have false positives. I'll point out a couple. The Backstreet Boys are in here. How many of you have heard of the Backstreet Boys? Music pop group at the time. That's just random. It turned out that people talked about H1N1 and a new album release all at the same time. And so that's just a false positive. So this is the type of analysis that we'd like to do. And we've applied these graph analytics to looking at resilience of the electric power grid, some work joint with Pacific Northwest National Labs. And we've also applied between-us centrality, which looks for important actors within networks rather than the most connected within a network, to look at the human proteome. We looked at all the known protein-protein interactions at the time, built a network, and it turned out that the protein expressed with the highest between centrality has been implicated in breast cancer, but yet this plot I haven't really explained yet. We have degree distributions on a logarithmic scale on the x-axis and the between centrality score on the y-axis. And over here, this is a protein that's kind of like a needle in a haystack. It's very important, yet it doesn't interact much with the others. And working with clinicians at Emory University, we've gone and suggested looking at cohorts of some of these other proteins. So this is the type of science that we can do with these graph analytics. My group has supported a project that we call STING, that stands for Spatio-Temporal Interaction Networks and Graphs. And many of the globally significant grand challenge problems can be modeled by graphs that change over time, where the vertices represent either objects in space and time, and the edges occur and change over time. For instance, we can look at trying to discover community structures in large networks, trying to defend nations against cyber attack and also give attribution to those attacks, looking at influence within social networks, understanding and discovering insider threats. For instance, we worked on a DARPA project called Atoms that was motivated by the Fort Hood shooter, Major Nidal Hassan. This was an Army psychologist, fully cleared, had a clearance, knew all of the security procedures of the military, and yet he had a morale issue, and eventually over time he came in and he killed a lot of people at Fort Hood. So he broke no rules up until the point of doing an egregious act. And these insider threat problems, whether it's a disgruntled employee or one that is leaving and taking company IP or destroying information internally, you'd like to be able to find these egregious events before they happen, while the actors may be acting alone and know all of your procedures and security procedures as well. So these are the important types of problems. I've talked about detecting and preventing disease in human populations. So what's the challenge for us as computing professionals? It's really the fact that this is an emerging space. We often have to map from that application domain to algorithms and architectures. And our lab has been very early at doing hardware-software code design, because many of the traditional problems and machines that we have don't work well on these problems. There is sparsity in the data sets and lack of locality in these graph algorithms, and even parallelizing these algorithms for massive streaming data analytics and looking at energy efficiency at scale of these problems becomes a challenge. We are a performer in the DARPA HI program. This program is about 1 year old, and it is the hierarchical Identify, Verify, and Exploit program. And our project is called SHARP, or Software Toolkit for Accelerating Graph Algorithms on High Processors. The DARPA Hive chip is a proposed design where either Intel or Qualcomm, who we're partnered with, will produce a chip that is much more efficient, maybe 3 orders of magnitude faster for graph algorithms. And we are working with Pacific Northwest National Lab and Northrop Grumman, as well as Intel and Qualcomm, in a collaborative environment to design algorithms and workflows that perform very well on these new architectures. So you may not see this chip next year, but this may be the chip that's driving your cell phone all the way up to your supercomputer in 5 to 7 years' time. We also are the recipients of one of the first EMU-CHIC machines within academia. Our Intelligence Committee Advanced Research Projects Agency, or IARPA, has given Georgia Tech an award to have an EMU-CHIC that is a multi-threaded architecture designed by Peter Kogi and others that does the opposite of what current machines do. Instead of going out to memory to get data and spend all of the time to pull that data into the processor where you work on it, what this does is take fine-grained threads and moves them into the data system, and in that manner creates a faster, more efficient machine when looking at graph analytics. So we're exploring this machine. We have some applications running on it already, and it's really a fantastic type of new direction that we see in architecture. So if you're interested in solving new problems, this is a great time to look at architectures. There's room for innovation as the business community moves into the space of graph analytics to really ride that investment and figure out the best machines for machine learning, graph analytics, and these data science problems. This may be a convergence, sort of the confluence of these technologies, where we may be able to influence it from the scientific community to make sure that we have the best machines available in a few years' time. So Stinger as a project is ongoing within our lab, and we have really a decade of history. This is a timeline going from left to right, where we thought about these streaming graph problems and realized early on that this is much more challenging than we initially thought. And over time, we've come up with a data structure and algorithms that work well on streaming graphs, and we've been able to produce software and actually make a difference on a number of real-world challenges, and it's been an exciting journey to take. So Stinger has this notion that these graphs change over time. And what that means is if you think about learning graph data structures where you have an adjacency list, an adjacency matrix, you always start by thinking about how many vertices do you have, n, and allocating your data structure. Well, in these streaming problems, imagine you're running for years at a time. You have no idea how many vertices you'll see, no idea how many edges you'll see. And so you have to come up with ways to handle edges being inserted into the graph, edges being deleted, and keep that data structure up to date as you go. And so this is just the notion that edges come and go. And this gets us to really the heart of what we're trying to do. Traditional high-performance computing often takes a massive data set and analyzes it. So for instance, in your organization, when you have a cyber attack, you collect up all the system logs, you centralize them, you turn those port connections into a graph, you decide a particular machine was compromised, and then you often work backwards to tell the history of what happened. And that's really reporting on the news. Where we want to get is predicting the future, predictive analytics in the streaming sense, where you're not focused on the exact data set. You have some history that you've collected up, and you're taking that stream of updates to try to get in front of the problem and respond often in milliseconds to updates or flags. So for instance, if I'm doing a cyber analytic application, I don't want to wait hours to see an edge inserted into the graph. I need to be able to have that edge inserted, an analytic run or updated, and if that is an attack, maybe it's delivering malware, etc., I need to be able to block it in millisecond time, and if it's a good packet, then let it go on through. So I can't hold things up, and that's where I get to this predictive analytic. So many problems lend themselves to being able to work in the streaming domain. So as I mentioned, we came up about a decade ago with a data structure called Stinger, and the idea, I'll just put it up here, it's an eye chart. You don't have to, there's no quiz, so you don't have to memorize it, but it basically is a way to have vertices in a block over here with attributes to the vertices, and then edges come in blocks as well. and I could have vertices of different types and edges of different types, and some sort of physical to logical mapping, a one-to-one mapping between a vertex and maybe a logical index into this array. This is also extensible because for some applications, I may want to save information. So for each vertex, I may have a timestamp when I first saw that vertex. I may want to keep track of the number of edges that come into a vertex or its in degree, the number of edges that leave a vertex or its out degree. In other applications, I may not want to waste that space and just recompute it on the fly when I need it. And the same with edges. I can customize the edges in some way. So this data structure has allowed us to have the ability to have a graph, a massive graph, if you will, running on big supercomputers, all the way down to small versions that run on Raspberry Pi. And I use the memory of that system to hold the graph. And I imagine that there's one writer process, one update to the graph, one process that's continually writing to it. And at the very same time, I have multiple analytics that can attach to that graph, treat it as read-only, and update their analytics. So this is a very different workflow than traditional supercomputing, where we think about our code and we think about our data set, we put them into a interactive or batch queue, we run, we get an answer, decide what to do. This is very different in that the workflow is truly streaming. And one way of working through this is that we get a batch of inserts and deletes into the graph. We may have some time to pre-process, sort, and reconcile, and that could be everything from 10 edges to 100,000 edges. For a particular application, we could tune that batch size. And then maybe in the graph, in steady state, we have to get rid of things over time. So we may age off vertices or kick out vertices that are less important. If we haven't touched them in 10 years, maybe they're so dusty we can just get rid of them. We update the graph over here, and then we look at changing how the graph changes. And the hope is that we can update analytics on the graph rapidly in time proportional to the size of the update, rather than boiling the ocean and rerunning a new algorithm and running it from scratch. And then there's some change detection over here, and we go through a cycle of updating the graph on different analytics. We have a whole software stack that's put together, and the details here aren't as important as knowing that this is the graph. We have methods to ingest into the graph. We have analytics, some of which can call other analytics, and then a way to get some output, often going to a human in the loop who is able to use that information. So this is a workflow that we've stood up, and we have designed a number of algorithms that are able to operate on the streaming graph, from clustering coefficients. That's a metric based on counting triangles around vertices, and often is used to very quickly decide whether or not there are communities that are centered around sets of vertices. Connected components, or tracking them as the graph changes. I already mentioned betweenist centrality over time. How in a changing network do you understand who is the most influential? How does that change over time? Is there someone who wasn't influential before and all of a sudden they look like they're a leader? And there's also algorithms that we haven't really thought about before because there's been no research on these dynamic graphs. For instance, in a community, I may have a person who's central or core to that community. I want to decide anytime they have moved to be core of a different community. Or I may want to be able to track the formation of new communities or watch others dissipate. And so I have some fully dynamic analytics that we're also trying to design and discover new analytics. A lot of this work you'll find online at stingergraph.com. And I won't go through all of these quad charts. Each one of these could be a talk on the different algorithms that we have. But one of them I'll leave up for a second, incremental PageRank. How many of you have heard of PageRank? So this became popular because it was the first method that Google used to look at importance of the web graph, looking at the hyperlink structure. And it turned out when Google had an update, new web pages, new links, they would rerun the entire PageRank. And everyone who needs to update PageRank today runs PageRank from scratch. And often that's done either nightly or weekly because it's such a challenging problem to run. We have just designed with my research scientist, Jason Reedy, the first incremental PageRank. So the algorithm is elegant and the implementation as well. It turns out that there's a very elegant derivation of this that we've come up with in the last year. And it also runs very, very well to look at just the updated links and doing the updates just around that portion of the graph to find the new PageRanks versus running the entire PageRank on billions to trillions of vertices. So that's quite impactful. In fact, industry and laboratories are all clamoring to get access to that. Everything, I should mention, that I talk about, all of the code and is freely available from our website. In fact, I'll just move ahead quickly. We have stingergraph.com that has a gateway to code, documentation, and we have contributors and users from national labs to financial institutions, other universities, etc., that are using the Stinger software. And we have two repositories for development. One is the academic repository. This is at a GitHub at the bleeding edge of research, where new things that we implement with students go there. No promises made. It either works or it doesn't. It's academic code, no support. And then our partners at the Georgia Tech Research Institute, or GTRI, have an enterprise class version where they have made this rock-solid enterprise class, and this is what you need if you want to have a supported version and really do enterprise development with these streaming graphs. So just to summarize, this is an exciting area to be in. There are so many applications, from cybersecurity, health informatics, understanding world population, driverless cars, you name the application, there are places where graph analytics can help. And co-designing the architecture with these types of algorithms often leads to six or more orders of magnitude performance. So energy efficiency is the name of the game. That's really driving the limitations in this area. Understanding workflows of streaming algorithms is a hot topic. And also, as I mentioned, this confluence of high-performance computing with data science and machine learning is also quite an interesting space. So just to conclude, I have a few research scientists, Jason Reedy and Oded Green. Oded's headed to NVIDIA. A couple graduate students who are active, many who have contributed to the work here, some of whom have just graduated. In fact, this last year, these were my 9 PhD students. I'm really pleased that I have 6 of the brightest women at Georgia Tech, 3 bright men, and some of them have just recently graduated. In fact, Emily, Anita, Isha, Louise have just graduated this last year. So I'm looking for students. It's a great group, and I really thank them for the wonderful results that I'm able to talk about here. Lots of publications, and let me just skip through for the sake of time. Really acknowledge again the support that we've had over many years for the work that I talked about today. So thank you for your attention at this public lecture. I really appreciate your attendance and your attention to all of this work, and I'll open the floor for questions. Thank you.
Okay, thanks to you for this wonderful lecture.
Thank you.
And so we have time to take questions. So, anyone moving? Yes?
Facebook user. No, Yeah, it's quite scary actually what we're talking about. I mean, all this data are available, and okay. The first question is Facebook using already your strategy of this graph? So how? Because you're talking about your school, but at the same time there is Google. They have these pages coming in the first place and the second place. It depends, and also Facebook. Where you get this data, for example, from Twitter, is it available like this? I just so scared I will never use it anymore.
So
It's a public question.
So very good question. Where do you get data to do research? When I mentioned Twitter, at the time, all public tweets were publicly available. We have not looked at private data in this research. So all the data sets that we've used that I've talked about, we take from public sources. There are graph collections that are out there, and if you send me a note or search around the internet, you can find some. Your Leskovic at Stanford has a great collection, Kaggle. You'll find a number of data sets out there. We also develop on synthetic data sets. As was mentioned earlier, we worked on a benchmark called Graph 500 that constructs a synthetic graph that is very easy to implement that we use for testing. It's not a perfect generator, but the thought is if you can quickly create a massive graph, you can at least test your algorithms. And if they work there, there's hope on the real data. If they fail there, you have to go back to the drawing board. Academics often have a challenge getting access to real data, which is why we partner with industry and government, because every organization out there has data. Rather than expecting that it comes to us, what we do is we take our algorithms and methods to them and to the data. That way it stays in its protected or private environment, and we are really going to our partners and working with them rather than pulling the data to us.
Yeah, I find these graph algorithms interesting, and I know that many of those problems have also randomized algorithms that are really neat instead of deterministic ones. And I'm just interested if any of those randomized algorithms are actually used in practice, or it's mostly deterministic ones.
So it's a very interesting question, randomized and deterministic. Often those are used to look at a static problem. In this case, if you think about it, we don't have an elegant classic computer science problem. We have a data stream that often has noise in it, bias as to how it was collected, maybe different data streams that we bring together. And so it's an open question, what does it mean to be deterministic in that space? Because everything that we're doing is somehow non-deterministic from the order that we put things into the graph and the order that the analytics run. What I didn't mention is a whole other talk on some recent work where we look at the graph being updated at the very same time analytics are running. So imagine you're running and you look and you see an edge and you're running your algorithm and you come back and that edge is now missing. What does that mean? And so when we talk about deterministic versus randomized, it really is a different space where everything that we're doing has this non-determinism. So we have a model that we've just come up with for reasoning about the validity of our algorithms, something that makes sense. And at the end of the day, we're working on problems where we can't wait for the theory to catch up. We are helping people, making the world safer. We just have to do it, and we're trying to bring the theory. In fact, one of my students is a theory student, Chung Xing, who is looking at models so that we can reason better about the algorithms. Very good question.
So related to that, how much can you trade accuracy for speed?
So accuracy for speed, we actually, that's a very, that's a huge trade-off in some cases. So we've looked at tracking connected components over time. The jet lag is still with me. So I'm picturing a connected component, and we can actually trade off and run for a while. Maybe for accuracy, we can say, for instance, 97% of the time we are running well, we're running fast, but we can say we're accurate. And then maybe once a day we just run from scratch, and that is the correction in case we made a mistake. So adding edges to a graph is usually not as challenging as removing edges from a graph. That's where some of these algorithms run into some issues. And so we do make those trade-offs all the time.
Okay.
Other questions?
I find it interesting that you throw away some data when you say, oh, maybe this vertex is no longer important or this edge. And I was wondering, when you throw it away, do you lose completely information that you had, or do you retain it so that later on you can retrain your model so that it doesn't do the same mistake again?
So that's a very good question. And we're working in a number of problem spaces where they may have long, long histories. And the importance and usefulness of the information that gets brought in and the timeliness of it. So in many of these applications, old data, for instance, if we're trying to figure out a breaking event today, data from 10, 20 years ago may not be important at all. So for a particular problem and domain, we have to think about what is the right amount of information we capture. And when I say age off, really the current research is not just doing a time window to throw old stuff away, but it's figuring out what is less important. So if there are, to me, the way I reason about it is if there are parts of the graph that I'm always touching on an analytic, no matter how old they are, I don't want to throw it away. But if I have some fringes on the graph that are collecting cobwebs that are so old and I've never touched them in an analytic, what does it matter that they're there at some point? So I think this is a rich area of investigation. Very few have looked at what happens in these problems over long periods of time when I can no longer hold all of that information.
Okay, other questions?
Hello, David. Thanks a lot for this great talk. I was just wondering, when one does all this data analytics, is then most often evident was the right decision to take, or can you comment on this? Because it may not be easy to then look at data analytics and take the right decision all the time.
Right, so how do you know what is the right decision? The hallmark of these problems is often very different than what you see in the traditional machine learning crowd. In machine learning, I like to describe it, you're looking for big correlations, you're looking for clusters, and you're willing to throw away the noise because you expect there's a lot of power and you build models off of those big buckets. Here, in the decision-making process, I'm often looking at the end of a long tail. I'm looking for that one edge or that one event that may be rare but extremely important, and I don't want to miss it. And I like to describe it as having no false negatives. I don't want to miss anything. And then taking the false positives, that may be 10,000 hits, and bringing that down to just a few. So reducing my false positives drastically. And it's that mindset. So this, as I mentioned, this decision-making system has been used to try to identify insider threats, to looking at breaking events, and to helping analysts as a semi-automatic way for them to make better decisions. So the successes are really anecdotal in some sense, but this is really providing a tool that we're going to need a lot more of in the future. And so it's really open for investigation. How do we characterize in this space how good these decisions are?
I had a question about the whether scale, I see 450 million users, and I wouldn't be surprised if some of these models were able to run at that number of vertices, and you also already mentioned in the introduction a billion edges. Do larger graphs help in identifying that single thread or that single piece of information, or not?
So, very good question. Does the size of the graph essentially become overwhelming that you have too much information, as I understand it? So, you have to think about this different than the machine learning space. The graph that I have isn't just a model, and I have big models and small models. The graph is really the real information. And if I'm looking for fine detail, I'm looking for this one suspicious link, or this one malicious actor, or this one path that causes a disease that's a rare disease. I really am trying to save that fine information. So don't think of it as a machine learning graph and model or neural net. Think of it as this is your connections of your raw information, and I'm looking for those really unique patterns or the fine feature and fine detail. So I can't just agglomerate it in most cases and throw it away. I really want to save that information because that's the very important aspects that I'm looking for. And so the larger the graph, the harder this is to run these algorithms. Here's an anecdote. When you design an algorithm in this space, often you'd be happy if you made a mistake 1 in a million times. And for most people working in graphs, 1 in a million, that never happens. And if it does, you look at that one mistake, you say, that's an anomaly, you throw it away. Once I get up to billions and trillions, 1 in a million accuracy for an algorithm, I'm going to be inundated with mistakes. And so in this space, I really have to work on higher fidelity algorithms because no longer is 1 in a million good enough. I need 1 in a trillion type of accuracy. So that's another area as we push out, and many real-world problems are in the scale of billions to trillions of edges in those graphs. I need to work on the algorithms as well and make sure that I have this much, much higher fidelity. Thanks.
Hi. You mentioned that you remove or add vertices or edges. Does this modification of matrix and arrays take significant computing time?
So, very good question. You're asking about the modification of the graph as we add and remove edges. We've run a number of experiments where we use a static data structure on the graph, and then we use this modifiable data structure that we called Stinger. And the overhead of using this modifiable graph is actually negligible. So the data structure itself is really just a way, it's not rocket science, but it's just a way to do the bookkeeping so that we can add and remove edges as we go. And it turns out, much to our surprise, some of our early work 10 years ago was looking at batch sizes and updates, and it turned out that that wasn't a major concern. We thought it would be, and it turned out to be much of a non-issue. Of course, you have to implement it well, and I should say we have a derivative of this work, Stinger, called Hornet, where we have specialized this data structure for NVIDIA GPUs and other accelerators. And so if you know the architecture that you're on, there's a lot of best practices and performance improvements that you can make given a particular architecture.
So in terms of algorithmic complexity, it's order of 1, this modification on the graph? Or?
I mean, essentially, we try to make the updates in, amortize constant time for adding edges and vertices,
independently of the size of the
Correct.
Graph.
Yeah.
So we can take a last question.
From all these sources of information that you take, how do you extract the data that you find important and you pass it to the format that your graph accepts?
So that's an excellent question. So we're working from a variety of domains, and this is where we need data scientists. Right now it's myself and my students and colleagues, where we'll sit down with an analyst who may have spreadsheets and different types of data sets and say, okay, this is a vertex, this is an edge. For instance, in the problem of homeland security, we're working on protecting special events, and we have lists of homegrown violent extremists, public lists from the newspapers, and it has a name and an address. Well, is that address a vertex, and I connect the person to that vertex, or is the address an attribute of a person? And so we have to make a lot of decisions based on the algorithms that we want to run on the data that we have as to what is the right either ontology or schema to put it into this abstract graph. So what is a vertex? What are the different types of vertices? What are attributes? Are there timestamps? Are there weights? And so that's where we need data scientists, and really that's the interface between the application domain and the computer science is figuring out how to go across that boundary. And every single problem that we've worked on, it's different. And so there is no cookbook formula for that. That really is where the hard work takes place to be able to translate and figure out which is the best representation within this type of framework. So thank you again for your attention at this public lecture at PASC 18. I really appreciate this evening with you.
So we'll thank you again.
Thank you.